Tangent planes, linearization, and total differentials. Explaining tangent planes, I want to do two examples side by side. Example 1, example 2, and so example 1 is x squared plus y to the third plus z squared. It's an implicit, basically implicit function at one end or surface, and the other one is z equal to x squared plus e to the power y at 1, 0, and 2. So we learned that if all the variables in one side and it's implicitly defined and only constants are on the other side, and then you can name this basically function of x, y, and z, and then you find the gradient of that, and that would be the normal vector to the plane. And over here also I can rewrite this as z minus x squared minus e to the y equal to 0, and then instead of having the lowercase f, which was function of 2 variables, I will have function of 3 variables. And again, both of these surfaces are going to be the level surfaces of the function of 3 variables. So if I find the gradient of that function of 3 variables, it's going to be basically normal vector to the tangent line at those points. Gradient of the first one is going to be 2x 3y squared and 2z. Evaluate at 1, negative 1, and 1, 1, negative 1, and 1, and that will give you basically, it gives you 2, 3, and 2, and that one gives you, let's evaluate the gradient vector. That's negative 2x, negative e to the power y, and 1. And you evaluate at 1, 0, and 2, 1, 0, and 2, and what you get is going to be negative 2, negative 1, and 1. So in here, what you do to find it, again, side by side, example 1, example 2. In both cases, I had to set it up so all variables in one side, and then I find the tangent, find the normal vector. Normal vector found, finding the tangent plane is just dotting the normal vector by basically by the vector on the plane, setting it equal to 0. Same thing here, negative 2, negative 1, and 1, dotting it at x minus 1, y minus 0, and z minus 2, setting it equal to 0. So the tangent plane is going to be 2x minus 1 plus 3y plus 1 plus 2z minus 1 equal to 0. And in this case is negative 2x minus 1 minus y minus 0 plus z minus 2 equal to 0. Now, linearization in the first one is going to be linearization at the point 1, negative 1, and 1. So points around there at x, y, basically, and z is going to be basically solve for z in here, and so you get 2 plus 2 times x minus 1 plus minus 3 times y plus 1. And for this one also you get So for z, and you get 2 plus 2x minus 1 plus y, basically. Now, so that is going to be the linearization at the point 1 and 0 of x and y, basically. Okay. So now, if I want to find a very close points to 1, 0, and I want to find the z value for that, then I can use this linearization. And same thing, points that are very close, this time I have to consider z, because otherwise z can have 2 values for the x and y point, basically. I will go around that point and I find it. So all I did was that I went to the tangent plane and I saw for z, and that's the linearization. This one is a little bit more, it depends on that localization and z value counts, and this one doesn't, and we're usually asking you for a function and linearization with a function. Now, how do I figure out the total differentials with this? With total differentials, you just solve for basically z minus z0, or in here was z minus 2, and then you don't change the when you were subtracting the point to make that vector, you don't change that, and so you solve for this, and you're considering this as delta y and considering this as delta x. And so you can go from one to another, and here is y minus 0, so delta y is itself, this one is delta x. So basically here the dz is going to be equal to basically 2 delta x plus 2 delta x plus delta y, and over there dz is going to be equal to negative 2 delta x minus 3 delta y. And so that's the story of, oops, I think I went down a little bit. So that's the story of how this thing works out. So basically you find the gradient vector, you find the tangent plane, then you use the tangent plane to linearize, or you can use it to find the differentials. Also, differentials are looking like this, and so what you did really in here is you did dz equal to basically f sub x times delta x plus f sub y times delta y. And so sometimes that one is easier than the other method for the total differentials, because also you can have dw, where w is a function of 3 variables, and then dw becomes f sub x times delta x plus f sub y times delta y plus f sub z, or times delta z, if w is equal to f of x and y and z, basically. So yeah, that's the overall working them all out together.